Hello everyone, can you hear me well? As you can see from the title, we are going to discuss some practical aspects of implementation of QLDPC codes. So this is a joint work with Gleb Kovachev. We are from Lomonosov Moscow State University. We also have a cooperation project with Huawei Technologies, where we mostly work on classical LDPC codes, and as a part of this work we participated in 5G standard, and where we proposed one of 5G LDPC matrices. And so today's talk is like engineering point of view to designing good quantum LDPC code. So first I will give some brief introduction, and then I will discuss some decoders that I use to decode quantum LDPC codes. Then we consider some new code constructions that we proposed in our work. And finally, we'll discuss some further work. Okay. So we are working with classical stabilizer code. So we have Pauli matrices, we have Pauli operators, and we use standard short notations. And as usual, the weight of a Pauli operator is just the number of non-identity components in the tensor product. So let us denote by Pn star the subset of Pauli operators with global phase factor equal to 1. And a stabilizer group is just a commutative subgroup of the Pauli group that's generated by some set of Pauli operators that we call stabilizer generators. And the quantum stabilizer code is just a 2K dimensional subspace of the n-qubit space. And the group that is generated by these stabilizers is called the stabilizer group. So I suppose that everyone knows these definitions. We interpret the elements of P and star as elementary errors, and we call it Pauli errors, and they corrupt the n-qubit state. So as you know, if we have a state that belongs to a code space, then we have two types of errors. So degenerate errors that do not change the state, and non-degenerate Pauli errors that change the state. As you know, the minimum distance is just the minimum possible weight of non-degenerate errors that commutes with all the stabilizers. And these guys are usually called logical Pauli errors. So during this talk, we will identify these Pauli matrices with finite field elements, and we also identify Pauli operators with the corresponding vectors of the field of 4 elements. And we also represent stabilizer codes with, that are defined by M stabilizer generator by the corresponding M times N stabilizer matrix over the finite field of 4 elements. For example, the famous 513 code can be represented like that. So the stabilizer matrix, we call the stabilizer matrix W limited if the weights of all the rows and columns are upper bounded by W. And the main class of codes that we consider in our work is quantum LDPC codes, and these are classes of stabilizer codes with W limited stabilizers matrices as the number of physical qubits goes to infinity. So, and I suppose everyone knows two classical examples of such codes. These are surface codes. They are 4 limited, and cover codes, they are 6 limited. And we use standard graphical representation for stabilizer matrix that is called tenor graph. It's just a bipartite graph with two types of vertices. One type corresponds to qubits, another one corresponds to stabilizer generators, and we connect a qubit with a stabilizer generator if it acts non-trivially on this qubit. And one of the most important and used algorithms that are used for general QLDPC codes is so-called belief propagation decoder. It is a kind of iterative message passing decoder that works on these tenor graphs. So if you don't know the belief propagation, so you can think about, for example, Sudoku puzzle. We have a Sudoku puzzle and we have some cells that are missing. So, and we have local constraints in Sudoku. And when we try to solve the Sudoku, we just look at these local constraints and try to figure out what the values are here using these local constraints. So this is what is like the belief propagation decoder. Of course, it is much more complex because for each qubit we have much more information usually. So why we use general QLDPC codes instead of topological quantum codes in this work? So I suppose that in this conference there were many talks that already discussed that, but I will briefly remind that usually such codes have much better rate, and actually this is maybe the main motivation behind using these codes. They also might have better minimum distance, but this is a major open problem whether we can have minimum distance much more than square root of n. And the famous recent breakthrough showed that it is possible to do fault-tolerant computations with constant overhead using some classes of general QLDPC codes. But if we look at this, at the known codes, at the known classes of generalized general QLDPC codes, you may see some problems with using them. So, for example, there are a number of really good theoretical constructions, such as Generalized Hypergraph Product codes, and they have some really nice properties when n goes to infinity. But if you want to construct something practical for lengths, say 100, 200, or maybe 1000, you have problems because I will show you that these codes are not the best one if you look at this range of the number of physical qubits. And also the performance of the proposed codes is far from the optimal under this under the variable decoders. Mostly these are BP decoders and some their modifications. So mostly this is attributed to two things. First, if we construct Tanner graphs, if you look at Tanner graphs of QLDPC codes, they necessarily have 4 cycles. But I think this problem is not really important because I will show you that it is possible to design at least CSS codes when in each part you do not have 4 cycles, and those codes works quite well on the BP decoder. So this is not a big problem. A bigger problem is that they have, since they are W-limited codes, so they have low weight degenerate errors, and this is mostly the main problem that causes that BP decoder, belief propagation decoder, cannot converge to any code word. So, and also, of course, we need to implement fault-tolerant gates, and it is not clear how we can do it in general QLDPC codes. In this work, we mostly will deal with two of these problems, with code constructions and with the performance, with a new decoder for these general QLDPC codes. So let's start from the decoder. In our work, we propose to use a BP decoder with a special post-processor, and that is called OSD decoder. So main motivation of using this OSD decoder is as follows. When you run the BP decoder, the main problem with it is that it doesn't converge to any code word. If it would converge to some code word, maybe a wrong code word, it would be much better than it, when it doesn't converge to any code word. And if you need to return your state to the code space, you still need to find some correction operator that return you to the code space. So you need to find the code word. And that is why we propose to use an OSD post-processor that guarantees that it finds some code word. And one of the reasons why it can work maybe is because each code word in QLDPC code, if you look at the nearest code words, then you see that these nearest code words, they differ from this code word just by a degenerate error. So it means that if you miss the correct code word with this decoder, so you don't lose anything, because you would obtain just another code word that is equivalent. And this can be a problem in classical case, because if you go to another code word, you would have what is called a miscorrection. This is a really bad thing in classical case. So this OSD decoder was introduced by Fossarier and Lin in 1995, but basically the idea of using information sets in decoding is quite old, as you can see, and this decoder can be used as a standalone decoder for classical codes, or it can be used as a post-processor for BP. And what is important about this OSD decoder is that it has near maximum likelihood performance for moderate code word lengths, say for example 100 or less. And if you look some tables that compare the best performance of linear codes, so you can find, you can definitely find something like BCH and the OSD decoder. So the standard classical OSD, so its main idea is to use what is called information set. So information set is just a number of positions of the code word that you can use to encode, that you can use as information bits. So you can use these positions in order to encode your code word. And the main idea of this OSD decoding is to use the available probability distribution for the code symbols to find their reliabilities. So, and then when you find their reliabilities, you can sort the columns of the parity check matrix according to these reliabilities and find the most reliable information set. And then, and you can do it quite efficiently with Gaussian elimination. So it's not a big problem. So if you use hard decisions for code symbols from this information set, so you can reconstruct a code word. And actually, you can stop here, and this is called OSD-0 decoding algorithm. But you can do even better if you use what OSD-m decoder, and it just flip the hard decisions in no more than m positions for symbols in T to obtain the list of code word candidates. And then you just choose among this list the most probable according to some channel model. So if you use binary symmetric channel, you use one metric. If you use AWGN channel, you use another metric. And here in our work, we use third metric that is related to quantum codes. So as I said, so we need to modify this classical OSD post-processor in order to use it with stabilizer code. So here you can see the necessary modification. So the input to this algorithm is a cost function, that assign a weight to each code word. Then we have a binary parity check matrix. We have a syndrome vector and an initial correction vector. So you can also take into account that here we consider syndrome-based decoder, because classical OSD decoder is not for syndrome-based. It's usually, so we have available information from the channel, but we do not have this for quantum codes. So the output of this algorithm is a correction vector. It's just a word that satisfies the syndrome. So we start from, we first find m linear independent columns using Gaussian elimination. Then we use all other positions as information set. And then we perform the encoding operator for this information set. And if we want to do OSD W decoder, then you can also find a set of bits, set of W least reliable bits, and you can just bit flip over them and look at all of them and find the best code word in terms of your metric. So it's a quite simple algorithm, and then you return your best code word. But in order to be used for quantum BP, we need some other modifications. First of all, we convert our non-binary vectors, Pauli operators, to the binary vectors. Please take care that here we use interchanging order, not the standard order that is usually used in quantum codes. And this is important for this algorithm. And we also convert non-binary stabilizer matrix into the binary matrix with 2 times the number of columns. And here we apply also quite non-standard approach, so we change the order of X and Z parts. And we do that because we want to obtain a syndrome just by multiplication of this binary representation of a Pauli error by this binary representation of this stabilizer matrix. That is the main reason. Okay, and finally we have OSD-w post-processing. So on the input we have stabilizer matrix and syndrome vectors, and the output is a correction vector. So when we run the belief propagation, we obtain distributions for each individual qubits, and then we make hard decisions, and if these hard decisions constitute a vector that satisfies all the syndromes, then it's okay. We just return this. If belief propagation fails, we calculate the qubit reliability, and we sort the columns of the parity check matrix in order of increasing reliability. And I will say about reliability measure in a minute. Then we just return the result of the classical OSD decoder that is run on this binary representation of the matrix. So here we use QSD, it's just a short notation for, so we convert to the binary representation our non-binary vector and non-binary stabilizer matrix. We run classical OSD, and then we convert back to non-binary representation. So, what are qubit reliability? So basically you can define it in many different ways. So one particular way is just to use the probability that we do not have any error. And this is kind of asymmetric in terms of this x, y, and z, and you can also use symmetric value. But it turns out that in practice, they have really similar performance, so it really doesn't matter what you use. For some codes, the first one works the best. For some codes, the second one. Okay, here are some implementation details. Maybe I can skip them. So first of all, we use non-binary BP decoder because we want to perform decoding for depolarizing channel when we have correlation between x and z. We also use log likelihood ratios. We use approximate version of BP. This is important because we also run some tests on non-approximate version, and we have even better performance. But in order to speed up the simulations, we used approximate version. And maximum number of iterations 32. And what is also important, we used what's so-called layered schedule. So it means that we process each check node not simultaneously, but one by one. And this radically increases the convergence speed, so it approximately 2 times. And what is more important, for some QLDPC codes, we see that only this BP with this layered schedule also improve the performance by several orders of magnitude. And I should also mention that the additional complexity of this OSD processing is not that much, because you only need to run it when BP fails. But in good conditions, when you so your BP should work for the most of the cases. So that is why this additional complexity is quite small in practice. And here you can see some simulation results that we performed for some of the codes that we use. So here, here you can see that for some codes, for example, black code, you do not get much. And the reason of this, because for this code, BP decoder works really well. But for other codes, for example, HAR codes, that very well-known code on 3D grid, you can see that the BP performance is awful, not quite good. But if you use this OSD post-processing, that it improves by several orders of magnitude. And we also found our own codes that also perform quite well and have the same characteristics and even better characteristics than these HAR codes. Okay. So the codes that we used in our benchmarks, so we have 2 types of codes. First kind of is a generalized bicycle code that was introduced by Kovaley and Prudko. And we also propose some new big class of generalized hypergraph product codes that we introduced in our work. So we compared against several known classes of QLDPC code, such as hypergraph product code, surface code, and we use surface codes that would use in Bravey, Shuhara, and Vargo paper, where they used MPS decoder, and we compare its performance against MPS decoder. And we also used Hyperbicycle codes introduced by Kovaley and Prudko, and also homological product codes introduced by Bravey and Hastings. So here you can see some numerical simulations. Here you can see that this OSD order, somehow it helps. But mostly, for most of our codes, we see that basically what you need to do is just to use OSD-0. So it has a cubic complexity. It also works quite well. But for some codes, you need you can improve the performance by using a higher order of OSD. We also compared our approach with existing approaches that improve the performance of belief propagation, such as random perturbation enhanced feedback, matrix segmentation, and I should emphasize this matrix segmentation because it's quite new, and this paper appeared just 3 weeks before our paper. So it's quite new algorithm, and it's quite interesting. So I will show you that it works the best among all these three. Okay. And here you can see the simulation results. So we used one of our constructed codes, and we compared with the surface codes that has the same number of physical qubits, approximately the same number. But for our code, we have like 28 number times more logical qubits, and you can see that this red curve that corresponds to the surface codes, it intersects with the black curve that corresponds to our code. And this is a QLDPC code. The black curve is a QLDPC code, and you can see that even if you use one of the best known decoders for one of the best known codes for some fixed number of physical qubits, so we can still outperform it with OSD decoder, even for very large number of physical qubits. So here we used 1,200, approximately 1,200 physical qubits. So it's quite big surface code. It's not small surface code. So it's really easy to outperform small surface code, but not so easy to outperform long surface code. So its minimum distance was like 20, as far as I remember, this surface code. Okay. So here are some code constructions. So we have quantum CSS code, and as you know, it is usually defined by a pair of matrices, and they are not any matrices, and this is the main problem in designing good QLDPC code, that you need this constraint. So, and the dimension is given by this formula. And as the first part of our new codes, we used the class of codes that was proposed by Kovaley and Prudko, and they generalized bicycle QLDPC codes of Mackay and et al. So the idea is quite beautiful and simple. So we have two binary square matrices, and they should compute, and that's all. So you can obtain very nice CSS codes just from a pair of commuting matrices. We can generalize, so we can see if we, for example, use a finite commutative group, and A and B are just matrices that represents the elements of the group algebra over this finite commutative group, then of course these matrices A and B always commute. And this way you can obtain generalized bicycle codes that was proposed in Kovaley and Prudko paper. This way you can obtain quasi-cyclic CSS codes that also quite very well-known class of QLDPC codes. You just need to use a direct product of two cyclic groups. And you can also obtain this way Haag's cubic code. You just need a product of 3 cyclic groups. So let us return to the case when we have a cyclic group, just cyclic group. In this case, what we have is called the ring of circulants, so just circulant matrices. And as probably you know, that this ring of circulants, it is isomorphic to the ring of polynomials modulo x. So here you can see the formula. And we use this approach in order to find the nice dimension formula for these generalized bicycle codes. So it's very simple. It's just 2 times the degree of g of x, and this g of x also play very important role in designing these codes. And what is important about this? So if you are lost, so I am talking about a generalized bicycle codes that obtained from 2 commuting matrices, and these 2 commuting matrices are just circlants, and these circlants are defined by polynomial A by polynomial B. If you look at these polynomials, you can immediately calculate the dimension of the corresponding CSS code. And moreover, you can not only calculate the dimension, you can also find the structure of what we call the syndrome codes. The syndrome codes is just, if you look at all possible, at the linear space of all possible syndromes, they form a linear code, and in fact, this linear code in this case is just a cyclic code, and the generator polynomials for these codes are just defined by this polynomial j of x that we use to design this generalized bicycle code. And we can use this fact in order to design new generalized bicycle codes that also have a very nice feature that they have a protection in the syndromes, because their syndrome code are just cyclic codes. And if we, for example, use j of x, that is generator polynomial of some BCH codes with small number of errors, then you will obtain a code that has protection in syndromes. That this can also be used in faulty syndrome measurement, but it also helps in BP decoder, because it avoids, it gives you opportunity to avoid small trapping sets. So here you can see the simulation results. Here we compare Hyperbicycle code of Kovaley and Prudko and new generalized bicycle codes that we constructed. So they have similar parameters, and what is really important here is that we managed to construct generalized bicycle codes that is 5 times smaller, but it has absolutely the same parameters. In terms of minimum distance, in terms of weights of stabilizer, so it's 8 times less, but 8 times less number of physical qubits. And you can see that it performs almost the same under this new BP-OSD decoder as, for example, Hyperbicycle code that is also quite good. Okay. We also compare our codes with homological product codes, and we also so we see that this class of generalized bicycle codes are quite good, because so we have a script that you need just to run, and you can find codes that are better than the all known to us small codes available in the literature. For example, if you look at the example that was given by Bravey and Toll in his paper, so he used some small homological product code. So we managed to find a couple of codes just in a minute that has, for example, 6 times more logical errors and logical qubits and almost the same performance. So we also calculated the threshold for the depolarizing channel for these generalized bicycle codes, and we see that it is quite high. So of course this is not the threshold, it's like a pseudo threshold, because we do not have a proof that this class of codes has threshold. But actually what we see that they behaves like there is a threshold under this BP-OSD decoder. And also we compare this class of QLDPC codes versus toric codes and compare their thresholds. So you can see what is important here. So you can see that the threshold of the toric codes are better, but the actual performance, if you look deeper in water rate, the actual performance is usually worse. So the threshold is not an ultimate answer to the performance of the code. And so you can see, for example, in our main slide, here you can see that this surface code, it starts better, but then it intersects. So it means that the threshold is not the only thing that you should look at. Okay. Let me briefly describe our code constructions, our new generalized hypergraph product codes. So let R be a commutative ring with identity. We denote by M and MR their class of matrices over this ring. And we also we identify the elements of these matrices over the rings with the corresponding block matrices. Yes, so we have a matrix over some ring, usually some matrix ring, and we identify it with the corresponding block matrix. And for example, if we take the ring of circlets with the circlet size L, this corresponds to the set of quasi-cyclic matrices. So let me remind briefly what are hypergraph product codes. They are constructed from two codes. And so we generalized these constructions when these hypergraph product codes are constructed from square parity check matrices. So we suppose so here, so in the original construction, we do not suppose that A and B are square matrices, but in our generalization, we suppose that. But this is not a big problem because, as what's shown in the paper of Kovaley and Prudko, so we can still have this nice result about square root of n for such with such restriction, and moreover, the best known small codes, small quantum hypergraph product codes are obtained in this way, as usual. And as you know, the hypergraph product code is defined by this parity check matrices with this n and k. And they have very, very nice theoretical properties that you can predict their minimum distance. This is, so far for our codes, we cannot give any lower estimates, so we can only give upper estimates on the minimum distances. But we suppose that for some classes of our new codes, we can also maybe conjecture some similar lower bounds. So let me just briefly describe this new construction. So it's quite simple. It's just generalize this to commutative matrix construction. So we have what we have here. So we have a pair, a matrix B, and some set of matrices of the same size. And we say that to a matrix B and this set R commute if this matrix B commute with all matrices from R. So we have not two matrices that commute, but we have one matrix that and a number of matrices that commutes with this particular one matrix. And then we just use, so we construct a CSS code in this way. So it is, so here it's A is a block matrix. Each block is constructed from A's. And you should remember that A's commute with B's. So and we just use a block of so this matrix here, and you can see that in this way you can obtain as a special cases you can obtain hypergraph product codes that are constructed from square matrices, and as a special case you can construct some new codes that we used in our paper. So here, if you are interested, I can show you some particular matrices, but I suppose I don't have any time more, yes? So here just some simulation results, so you can see that this so we compare just this hypergraph product codes versus the generalized hypergraph product codes, and we see that they perform better. And we also have estimations of the minimum distance. We also see that we can construct these codes with better minimum distance. I should also say something about the deep simulations, because it's a real concern for LDPC codes that they converge, they perform well for like 10⁻�3, but when you go up down to 10⁻10, you would have problems. This is certainly true, but this is not true for these particular matrices and particular OSD decoder. So you can see, so we managed to simulate this BP-OSD decoder down to 10⁻10, and we do not see any problems here. So here's the conclusion. So we propose new BP-OSD decoder for QLDPC codes. We propose new examples of generalized bicycle codes. They have good finite length performance, and they also have natural syndrome redundancy. And we also propose some new general anzats, new general class of codes that contains many known class of codes like generalized bicycle codes, 3D Haar codes, the hypergraph product codes when they constructed from square matrices. And they also contain some interesting new classes of QLDPC codes, and these new classes are really similar to the classes that are used for classical LDPC codes. For example, if you look at Wi-Fi matrix or some matrix, so you can see that it also has some structure. So it's part of the matrix is fixed and part of the matrix is arbitrary. So in our construction we have something similar. Unfortunately, we do not know the minimum distances for these new classes of codes, but we have some conjectures about it that we can maybe prove. And we also don't know so far how to handle faulty syndromes. And thank you for your attention. And at the end of the talk, I would just like to show some really recent results. So we simulated our codes on single-shot BP decoder for phenomenological model, and we can see that it also performs quite well compared to toric codes. But this is only phenomenological model, and as you know, it is not really important, because basically you need to simulate on circuit-based model. Okay, thank you for your attention.
Okay, one or two quick questions.
Thank you for your talk. What you're calling the MPS decoder of Bravi-Suchar and Vargo has the property that if you don't restrict the bond dimension, it is in fact optimal with respect to Bayes' theorem. It's the best possible decoder you have.
Yeah.
How do you understand your decoder doing better than that, you know, in the context of this information theoretic bound?
I suppose that we have better minimum distance at least. So for our codes, so it's quite high, so we have some ways to estimate the minimum distance, but OSD decoders also perform like near ML. So if you look at, there are even theoretical results that suggest that this OSD decoder performs exactly as ML with some conditions, under some conditions for classical code. So it, I don't see here any problems, because if you take a code with a larger minimum distance and with a larger number of logical qubits, so why wouldn't you?
You had a fixed code with, I believe, 1,200 or something qubits. Your main result, you have a slide that you call your main result. Okay. On that slide, you show a crossing of your curve performing better than the optimal curve, and I'm just trying to understand that.
So what do you mean by optimal code? Optimal code is
optimal decoder. Sorry,
yes, it's optimal decoder, but maybe it's not an optimal code. So, so the main purpose of this talk not only about decoders, but we also invented some new ways how to construct new good codes, and we can see that this is not a really fair comparison, because for surface codes we have they are 4 limited, and we used codes that are 6 limited. That is why in this larger class of codes you can expect that the minimum distance could be higher than for surface code. So you can somehow maybe do better than this square root of n. But this is a practical result. This is not asymptotics. Yes, so for some particular n, so we managed to, so we see that we can design codes that have better minimum distance than for other known codes. So and even for surface codes. So it's just related to this stabilizer weight. If you would use stabilizer weight 10, you can do even better. So you can design even better codes.
Okay.
Yeah, there was a question there. Maybe let's just take this question and continue. Or yeah, there. Yeah.
How did you get to simulate 10 to the minus 10?
That's a good question. Yes. Actually, the reason I showed this this graph is because you might thought that this sounds like any other theoretical decoding algorithm that couldn't be run in practice. So, but as I said earlier, the complexity of this BP plus OSD decoder is mostly governed by the complexity of BP decoder, which it is possible, of course, to simulate down to 10 minus 10, and in our project in Huawei we do it every day. So you just need to use an appropriate decoder with SSE instructions and several cores, and if you run, for example, for a week, you can simulate even deeper than 10 minus 10, so it's not a big problem.
We're a bit behind on time, so let's thank Pavel again.
Okay.